Okay, assalamu alaikum everyone, and now I'm starting. So the last time we finished was on fractional distillation. So now we're gonna continue on to another separation technique, which is chromatography. So chromatography, like any other separating technique, uses the difference in physical uh, quantity uh, to separate substances. So the way it works using capillary action. So what is capillary action? Capillary action, if we use the book definition, it is the ability of a liquid to flow in narrow spaces without the assistance of or even in opposition to external forces like gravity. So to understand this much more clearly, you can take the example of, let's say, a tissue in a petri dish, and if we put even one tip of this tissue in a petri dish full of water, the water will start traveling upwards in this tissue by capillary action. So we would usually say that the tissue is absorbing water, but it's actually traveling upwards by the help of capillary action. And the same thing happens if you put a very narrow straw or glass tube in water. Wa- uh, so the water will also flow upwards in the tube using capillary action. But then why does it flow up? Because gravity is pushing it down. Then why is it opposing gravity? So gravity is an external force. So in the definition, they say even in opposition, which is mostly for the benefit of gravity. So what they mean by this is that if gravity is pulling down on everything, so it's the downward force, there must be a force which is opposing gravity, which is forcing the water upwards. And that force is the attraction between the glass wall and the water. So if if you even pay attention to the diagrams in questions, and if you have been to a laboratory and done this experiment, you will always notice that water curves like this, right? But I'm going to get to this later. First of all, we were saying that when we put this tube, so I've zoomed in, we put this tube in water, and according to capillary action, the water is going to travel upwards. So this is because the water molecules have an attraction between each other. So they have attraction between each other, and they also have attraction between the glass walls. Okay, so there is a force of attraction between every object, like my hand and this pen, the glass tube, wall, and the water. These are called van der Waals forces. So, but some of them are stronger and some of them are weaker. So the water uh, gets attracted to the glass wall much more strongly than it is getting attracted to each other. So that's why it travels upwards. So now once it has traveled upwards, you'll see that it you wouldn't expect the level to be flat like that. It's going to be like this. So this is called a meniscus. And also keep in mind that whenever we take a reading, so let's say that this is graduated. So I'm going to take this reading, bottom of the meniscus. I'm going to take the reading from the bottom of the meniscus. So the reason why this meniscus is formed is because the water has a greater attraction for the glass walls than itself. So they're all kind of trying to reach up to those walls. You see, they're just like spread out like that. So their attraction between the glass walls is the attraction between water and the glass walls is stronger than water and other water molecules. So then moving on. I'll also give you another example of mercury. So, mercury, first of all, has more affinity for itself than the glass walls. And this is why mercury never travels by capillary action. And that's kind of confusing because in thermometers we use mercury. And I just said that mercury never travels by capillary action. So the reason why we use it for thermometers is because in normal conditions it's just gonna stay in this bulb, but if we heat it and if it has no other place to go to, it's gonna rise upwards. And so until and unless it doesn't have absolutely have to travel up this tube, it wouldn't, because it has more affinity with itself than for the glass walls. And that's why its meniscus is curved upwards, unlike the water, which was like this. So its meniscus is curved upwards because it's kind of pulling in on itself. So that's why it forms this domed shape. Okay. And so because it would only travel up the tube uh, when it absolutely has to, and it's given energy and it expands up the tube, that is a benefit for us, and that's why we use it for thermometers. Using this property, is there any other advantage that we have for using mercury as thermometer? You guys, anyone can raise their hand. It's a question. Using this property, how is mercury useful as a liquid to use in a thermometer? Rahim?
Yes. So the advantage is basically that we get a more accurate reading because the heat is applied to it at a specific temperature. So it would go up according to the heat energy it's being provided.
Yeah, that's also an advantage, but using the property that it has more attraction for itself than the glass walls. How is that beneficial for us?
It it wouldn't move. It wouldn't move up. It wouldn't move up. The mercury wouldn't move up the thermometer because it has more affinity for itself. So it will be pulling down.
It wouldn't stick to the walls, right? Like, you know how when we pour, if we used water instead, water would get stuck to the capillary walls because it has more attraction to the glass wall than itself. Mercury does not get stuck. So that is one advantage that we have for using mercury in a thermometer. Okay, so then coming back to chromatography. Uh, so chromatography, the
Sundus, okay, I just want you to ask them what did they understand by capillary action?
oh, okay. So whoever wants to answer that question can raise their hand.
What did you guys understand by capillary action? And Sundus, just a minor correction, if you don't mind. Capillary spelling, single
Uh,
P I double L.
so single P and double L.
Yes.
Okay, thank you.
Okay. Momina wants to answer.
Momina?
Yes, so
So,
I understood that capillary action is the attraction of water molecules to um, the 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 tubes of the glass tube. So that's why it moves upwards without any other force, like gravity.
Yes, very good. See, capillary action is to be in simpler words, basically when the attraction between different molecules is greater than the attraction between similar molecules. So what Sundus is trying to explain us is that it is due to capillary action that the water or any solution rises up a paper. Okay, so that is because the attraction between the water molecules and, for example, the tube, you know, in the example that Sundus was showing us, the attraction between the water molecules and those glass wall of the tube is greater than the attraction between the water molecules amongst themselves. And that is why the water molecules cling onto the walls of the tube. And that is why you see the meniscus are dipping downwards, because the molecules at the side are clinging onto the wall strongly. They're clinging. They don't want to let go of the glass wall, because the attraction between the water molecules and the glass wall is greater than the attraction between the water molecules themselves. Did you understand? Now, whereas in Mercury, the attraction between the mercury atoms themselves is greater as compared to the attraction between the mercury and the glass wall. And so you will see that the molecules are clinging onto each other rather than the glass tube. They're clinging onto each other. And that is giving the dome shape of the meniscus. You know, the upward curves in this. Can you show us?
Yeah.
Can you show us?
Yeah, just a second.
And so why is this property useful to be used in a thermometer is because if, for example, so you can see now these arrows, can you see the three arrows? Now the three arrows are showing that the attraction between the mercury atoms amongst themselves is greater than the attraction between the atoms, the mercury atoms and the glass. So they don't care about the glass wall. They care about each other. So they are trying to stick together. They're attracting each other. So that is giving that dome shape, the upward curved shape to the meniscus. Okay, and why is this useful in a thermometer is because if there was attraction between mercury and glass wall greater than the attraction between the mercury atoms, then the mercury would have clung on to the tube even when it should have shrunk. It would have, shrunk due to drop in temperature. So instead of shrinking, it would be clinging onto the wall, and then we wouldn't know if the temperature has gone down or not. We would still be able to see the mercury clung onto the tube, and we would think that the temperature is higher than what it actually is. Did you guys understand?
Yeah.
Yes. Okay. So now we know what capillary action is. So remember, now the reason why the mercury rises up the tube despite the gravity working the other way. Did you ever think that the gravity is pulling the mercury down, right, towards the bulb? If the bulb is facing the earth, I mean, the bulb is facing the ground, but it is still rises. Why? Because the attraction between the mercury and the glass wall is even greater than the weight of mercury itself. So the attraction is so strong. Okay, the attraction is so strong that that force, the attractive force between the glass and the mercury atoms is even greater than the weight of the mercury itself. Okay, so that is what capillary action is. When a fluid rises up a tube by virtue of its attraction towards the material of that tube, against its own weight. Okay, move on, Sundus.
So, chromatography uses the physical differences in properties between substances. So the first one that we discussed was capillary action.
Sundus, I'm so sorry to interrupt you, but also ask them, what is that physical property difference that we are using in chromatography? What physical property difference are we using when we are separating substances using chromatography?
I didn't explain them what chromatography was till now.
Oh, okay. So you go ahead and explain them first. Okay. Sorry.
Okay. No, it's okay. So we're gonna use the first one that we took advantage of was capillary action, and another one that chromatography uses is solubility. So before I go on with the list, I'm going to tell you what chromatography means. Uh, Chrome means color, and ography means writing. So it's basically color writing, and you'll understand that better after you see the method. So first of all, we're gonna take a filter paper. So this is the filter paper, and I'm going to draw a pencil line about like 1 or 2 inches above the base of the filter paper. So this is the datum line. Why? Because we place our data on this. So the data is the information that we already have. So let's say that I'm trying to separate um, black ink, okay, and I want to know what its components are. So I'm going to put a drop of black ink on this line, and I'm going to let it dry, and then after a few minutes put another drop and then let that dry. I'm going to do this because I want this spot to be concentrated. So first I want all the ink particles to be concentrated at that one spot. So once we're done with that, we're going to move on to the second step, uh, which is putting it in a beaker, okay? And we're also gonna cover it with a lid, so I didn't draw that here. So I'm also gonna cover it with a lid because we don't want any of our solvent to be evaporating off. And I'm going to make sure that the paper is just like the water level is below this datum line. It should remain below the datum line because the solvent we're gonna use is gonna be dependent on the type of substance we have over here. And if I'm, let's say, so over here I'm talking about black ink, that's why I'm using water. So if I'm using a water-based ink, water would be a better solvent for that. But if I'm using, let's say, a protein sample, like amino acids or something, ethanol would be a better option because amino acids dissolve better in ethanol. So it all depends on the kind of substance you have over here. So by capillary action, the water is going to travel upwards. So it's going to travel upwards and it's going to carry the ink with it because the ink is soluble in water, and I'm going to show you a video of this being carried out. But for right now, just stick with my diagrams. So the water will take the ink up. So the ink is dissolved in water, and when it gets dissolved in water, as water is moving upwards, it's getting dissolved, and it also moves upwards with it. So it moves upwards, and over here is the front line. So what the front line is that when the water moves upwards, it moves upwards like in a uniform way, okay? And when it reaches like about the end of the paper, so this is actually the line till which my water level has rose to, not water level, but the water that was absorbed, you can say, by the filter paper. So I'm going to stop, I'm going to take it out of this beaker when my front line reaches about the end of the page. So these substances have dissolved in the water, and that's why they also ran up with the water. Okay, then I'm going to take out my chromatogram, and this is going to be the front line. The front line is, as I told you, till where the water reach, and don't confuse it with the top of the color. So this is if you take this level, this is actually the rise of the blue color. This level is the rise of the pink color. So a rise, the rise is the height, or the height to which that color rose. And I don't know if you get this properly, but you in the laboratory experiment, you're gonna see the color as smears, because it's actually running up. You know how, like, you put, if you write on your copy with ink, and if water spills on it by mistake, how that ink bleeds all over the page. So this is actually happening in the reverse direction. In this, the water is traveling upwards, not downwards, and the ink is again bleeding out of that spot and running with the water. So it's getting dissolved with the water and it's running up. And this is how it's going to be if you carry out the experiment live yourself. But if uh, in questions, they just usually use it as spots. And so it's way easier for us to put a line and then measure the rise. And because this is a separating technique, the rise for each one substance is going to be unique to that one substance. So if I say that this blue dye has a rise of like 6 millimeters, and this has like a rise of 3 millimeters, this this substance will be the only one with a rise of 6 millimeters, and this is called the RF value. And I'm going to explain more about it later on. But yeah, first of all, if you do a real experiment, you do need to know where you're going to draw that line, from where you'll start measuring. So it's not like you're just going to take the anywhere on the blue and then measure the distance to the datum line, but you're going to see where the blue ink is more concentrated. So let's say if the blue ink is like more concentrated to the top, like right here, it's more concentrated over here. So I'm going to make a spot right here, and I'm going to run my line through it, pencil line. Always use pencil, because if you use ink, if you use a pen or a biro or felt tip pen or anything, it's going to have ink in it, and that also might run with the water. So I'm going to measure the distance to the datum line, and that will be my rise. And so now, another question that you might have is, why do they rise to different heights? So if I use the same example, so this is my front line, this is the datum line, and this is where the spot was initially. And if this was purple ink before, and now it has separated into uh, blue and pink, it's the purple ink ran up with the water and it separated into blue and pink. So why is the blue higher than the pink? So the pink dye rose to a lower level, right? It's lower than the blue. That means that it has more affinity for the paper, which is where the substances, you'll find the substances at stationary phase. So stationary phase is the phase of substances when they are solid or not moving, not necessarily solid, but they they are stationary. And the mobile phase is the solvent in which it was submerged, right? Like here. So that was the mobile phase, because it was that phase that made these inks run. So the pink dye had more affinity for the paper than for this solvent. That's why it got dissolved in the solvent till up till here, it bore with it, but then it just settled down and went back to the paper it loved. But the blue liked the solvent more, so the blue dye rose to a higher level, which means it has more affinity for the water, the mobile phase, than the stationary phase. So it likes to move. And so it ran up with the water and it bore it till here. And this is when it also stopped. Okay. So now, how are the so before, like, when I was talking about how the rise is specific to each substance, that is actually like kind of vague. I gave you a vague definition before. uh, I said that we're using the difference in solubility for this separation. So, and this is used for the identification of different substances. And so how we're going to identify the substances is by measuring the rise over run. So the level till which it rose over run, which is run is the the point till which the water reached, which is like the front, the solvent front. So this is actually a ratio between how much the substance rose in ratio to how much the water rose. That ratio is going to be fixed for one substance. It's that ratio which is fixed, not this the rise only. Because you could have a small chromatography paper and you could have a large chromatography paper, and the rise and run is going to be different, but the ratio will be the same for one substance. So that's how we come with the very simple formula for the RF values, that is rise over run. So
Okay, I have a question. If you
yeah,
okay,
sure.
okay. So the solvent that we have to use should dissolve the substances, right? Meaning the substances should be soluble in that solvent, right?
Yeah,
So preferably, if we have polar substances, the solvent should be polar,
yeah,
and if the substances are non-polar, the solvent should be non-polar,
yeah,
right? Right.
yeah.
Okay. And so please, after this, ask everybody what did they understand about rise and run, and what is an RF value, to make sure that they really understood.
Okay. Yeah,
Okay.
I have questions at then.
Okay.
Okay, uh, this is a very simple formula. R value equal to rise over run, and it has kind of like a nice ring to it, so it sticks in your head. But the one that's mentioned in your book is more elaborate and much more detailed. So distance moved by the substance over the distance moved by the solvent front. So I just put rise and run because it's way simpler that way. So how we calculate the RF values. If this is my chromatogram, so I've just carried out chromatography, and the black ink that I used has separated into this pink dye and this blue dye. And I drew a pencil line on the solvent front, which is my run. So it ran till there, and this is the rise of each of the substances. So my run, I'm gonna calculate that first. So that's the distance between the solvent front and the datum line. So that's 100 millimeters, okay, over here. And then the rise, for, let's say, the pink dye first. So I'm gonna make a line. So if this is all smeared over, but because this is a diagram, I just made a spot. If in real experiment, it's gonna be all smeared over. So the point where it's the most concentrated, I'm gonna take that, and I'm going to draw a pencil line through it, and then I'm gonna measure the distance between that pencil line, which is the rise of the pink dye, and the datum line. That would be 35 millimeters. So then using this formula, I'm gonna uh, calculate the R value. So the rise over run, okay, and the rise for the pink dye was 35 millimeters. The run was 100 millimeters, and so my RF value is 0.35. And once I get my RF value, I can open up my table where all the RF values are listed with their substances. So I see that the 0.35, the RF value of 0.35 is for safranin, which must be the substance over here. Now I move on to the blue dye. And again, if it's all smeared over and I want to see the point where it's most concentrated, I'm going to draw a pencil line, which is going to be its rise. And I'm going to measure the distance between rise and the datum line. It's 15 millimeters. Again, using the same formula for the RF value, 15 millimeters over 100 millimeters, and I get 0.15 as my RF value. And I again open up the table and I get to know that this is methylene blue. So that's how I can identify each of these pigments. And this is how I know that I know what the black ink is made of. Zainab, do you have a question?
Yes, I don't understand the run value. I don't understand what run is.
Run is,
Run.
yeah, run. So that is when, so before this this chromatogram was placed in a water beaker. So the water traveled upwards, taking the dyes with it. So when the water was running up, it was running with the dyes. So the dye you can see till where it ran, but the water ran up till here. So the level to which the water runs up or is absorbed up is called the solvent front. Zainab, did you understand?
Yes, thank you.
Okay. And did anyone else have a question?
I think Ahmed 31 also had a question.
Ahmed?
Yes, Ahmed, I'm unmuting you.
Ma'am, it happened by mistake.
Oh, okay. Okay,
Usman?
Usman.
Yes. Teacher, I still didn't understand that one.
You didn't understand what?
The run.
The
The
run?
run.
Okay. So I'll move back to this diagram. Wait. Okay. Okay, this diagram. So if you look at this chromatography paper, this is in a beaker, and the water is here. Okay. So the water is absorbed by the filter paper. That's the whole point of this experiment. So the water is absorbed by the filter paper, and it's carried up by capillary action. The level to which it rises to the level to which it runs. So we're going to personify this. Uh, the level to which it runs is called the front line. So we can also call it the solvent front. And then we can call it a run because it ran up, because it moves really fast.
So solvent front and run are the same thing.
Yeah.
Okay, and you know what? I think when you'll show them the video, it'll be clearer to them. They'll
Yeah.
understand what you mean. Yeah.
Yeah.
So yeah. So I would say that the front line is the upper limit till where the paper got wet.
Yeah.
Yeah, it's the upper limit till where the paper got wet. And you know, the color substances, they lagged behind. They did not reach the top limit of the wet paper, but they got stuck somewhere. Basically, you know, there are two forces. There are two forces playing their roles here. One is the attraction between the molecules and the paper, and the other is the attraction between the substances and the water, the solvent in which they are dissolved. So substances which are more soluble, or you know, they have greater forces of attraction with the solvent, they will go higher because you know they are running with the water molecules. So they are more friends with the water. So they will go a long way with the water molecules. And those substances, which have greater attraction towards the paper. Okay, so they will cling onto the paper, and so on clinging, they will lose their water. They will lose the. They will stop running with the water, and they will get stuck, or they will cling to the water as soon as cling to the paper as soon as possible. So they will be lower down. Am I right, Sundus? Is this
Yeah.
have I understood correctly?
Yeah.
Yeah. Okay. Good. Okay. Atika has
A
a question.
question.
Can you please
Yes.
explain the formula again as I got disconnected?
Oh, she's asking for RF value, I think.
Okay, so because we use chromatography for identification of substances, that's why we need that one value that is only like unique to one substance. So that is the ratio between the level to which the colored pigment rose and the solvent front, the run of the solvent. So that's the ratio between these two values, which is unique for one substance. So that is the RF value, and we calculate that by rise over run.
So can we also call it like it is the ratio between the distance that the water ran and the distance that the solute ran,
Yeah,
right?
yeah,
So it's the ratio, yeah. So it's the ratio between the distance that the water traveled and the distance that the solute traveled. That's the so rise is for the solute and run is for the solvent. You can write
yeah,
it down. Yeah. So the numerator, so the top figure is the distance that the solute traveled, your colored substance, and the denominator, which is under the fraction bar, is the distance that the water traveled. So that would be the same as the distance between the front line and the datum line. Is that
yes,
right?
yes,
Yeah. So your denominator will be the distance between the front line and the datum line.
yeah. Uh, Atika, did you understand?
Yes, thank you.
Okay,
Well, okay.
okay.
Yes.
So,
So Sundar, show us the video.
oh, okay, just a second. Let me just make sure that I'm done with this.